Okay, good morning, everybody. We'll give this a try. Always the joys of getting everything to work. Okay, today we're going to talk about linear discriminants. This is related to the Fisher idea, but it's taking it from a different standpoint. So remember where we were on Tuesday, where we said we were looking for an optimal projection vector that would do the best on a single vector to project the points onto it. We had a cost function where we wanted the distance between the means to be large, and we wanted the standard deviations of the individual classes to be small after projection. Well, we're looking at something similar here. And we're looking at Bayesian ideas, and we're looking at having a linear decision boundary. So it comes from the same idea, pulling in different topics we've already talked about together. So we know back from back from project 2 and stuff we did with the Bayesian classifiers, that when the covariance matrices in multiple dimensions are equal to each other, that all those squared terms go away. We're left with a linear boundary. Now, please nod your head. This sounds like you've actually been in this lecture once before. I can't see the people at home who are nodding their heads. Hopefully they are. Okay. So we're going to be looking at some of those cases, and so we can consider an identity covariance matrix scaled by something. So everything has the same covariance. Okay. The points are independent, because with a covariance matrix, that's the identity of a diagonal matrix. So it means the off diagonal, the covariances between features are 0. And if Gaussians are uncorrelated, Gaussians therefore are independent. So that same Bayesian stuff, where we want to choose the class that based on your measurement is the highest probability. Then with Bayes, we can turn it around to be the feature given the class times a priori. We divide by the probability of the feature, which we can cancel on both sides and ignore. This should sound familiar to everybody. Okay. And then we can take the log on both sides. Why do we take logs? It minimizes what else for logs? What other things do logs do? Right?
Round off, and they also help your sensitive have to get as much capacity.
Take care of round off errors, and we don't have the exponential. We don't need to do the exponentiation. And so we show in the bottom of the screen here what you wind up with in a 2-class problem, 2-class, 2 features. We say they're independent, so there's no x times y. And the e goes away because we took a log. This should start to be looking familiar to you guys. I know the first time I put it up there, all of you had just kind of glazed over eyes or what in the world? Hopefully now this is starting to look possibly understandable. And then all the same math, blah, 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 blah. And if we put all the x's and y's and the constant on one side and the zeros on the other side, we know that the squares are going to cancel each other. We're going to wind up with x times something, y times something, and some constant. Linear decision boundary. Y'all did homework number 3, where you were looking at things in 2 dimensions. You can see that decision boundary. It can be any conic section, including linear. It's linear when we have equal covariance matrices, because then the x squared, y squareds drop out. And whatever those coefficients are, they're blah, 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 blah. There's a whole bunch of X coefficients, a whole bunch of Y coefficients, a whole bunch of constant stuff floating around, a whole bunch of garbage. So it should be X times a constant, Y times a constant, and a whole bunch of constants. Linear. And we can then take them on one side and compare that to 0. If it's bigger than 0, make one decision. If it's smaller than 0, make another decision. We can take that same stuff and we can write it in vector form. And this is when your blood pressure and your sweat glands start working up. And I start saying we're doing things in vector form, and all of a sudden all you guys panic. You can do it. You can do it. You can do it. We can write it in vector form where we have two terms and a row vector and an X and a Y and a column vector. I just put a couple things on the board. I put them in the chat. Multiply these two vectors, please. Talk to your neighbors.
Yeah, Kristen, you're writing for the three of us, right? Perfect, sweet. He's writing for the three of us. No. Wait, what did you do? What? It's 3 times 5, 3 times 7. You get a 2 by 2 from this, right? No?
Row vector 3, 2.
Okay,
Column vector 5, 7. What's the part?
I think you knew what you said, but you had them. Yeah.
It's that linear algebra you guys are sweating about.
Gotcha. Okay. Yeah.
Yes, Taylor, yes. What do you guys got?
So we did, yeah, 29. So 3 times 5 plus 2 times 7.
I'm a realist. In theory, this is easy. In reality, you guys have too many problems.
In reality, stop caring about linear algebra after I took the final.
So the product of these two vectors is how much?
I never took linear.
Well, yeah.
29 is scalar. 3 times 5 plus 2 times 7.
The double E underground.
Okay? So now that you remember how to multiply vectors, look back here again. So we have this vector times this vector, this is X over Y. That's going to give us this term times X plus this term times Y. That better now? That's what W transpose X means. Where that X in bold is a vector XY, the X in bold is a vector X1, X2. If we're talking about the data for your project, what would that X be?
Evaluation data.
X1, X2, X3 down to X8. Mu 0, 0, or M 0, 0, mu 2, 0, mu 1, 1, blah, 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 down to mu 0, 3. That vector is a column vector, which has your data points, your feature points. Here is 2 points. It can be as many more as you want. W is a bunch of constants that come out from doing all this data stuff. Yes.
I don't understand your notation with the greater than less than signs and the column.
We're going to compare it to 0. It's
Oh.
a fact that I don't have it in computer form for the dot symbol.
I see. Okay.
So greater than less than is the comparison to 0. Somebody will type this up into equations. But because I'm not doing as much writing on the board, because we got so many people remote, You gotta put up with my typing. And then W0 is whatever constants you see all the constants are. Is notation better now? Few heads of all one. Anybody here that's a new museum that has a museum of presidential bobbleheads? It's in the news. So you can go and you can order them, you can go and look at them. They got one president for one bobblehead for every president. Aren't you lucky? What a great society. So we can take this algebraic thing and we can just define that to be a discriminant function. We are looking at a two-class problem. For the project, you are taking, for the project, you're taking that as a discriminant function and that as a discriminant function. But if we put everything onto one side, we can take that as a discriminant function. So we can compare G1 of X or we could compare this other G tilde, that's a tilde, tilde on top, G tilde, which is equal to this, which is equal to that, and compare it to 0. We can compare whether G1 is bigger than G2, or we can compare whether that's bigger than or less than 0. And since this is ugly, we're going to look at it this way. We can draw this in a diagrammatic format. We got W transpose X times W0. Which is the W1, W2 row vector, X1, X2 column vector, plus a scalar W0. We're getting out of here. We can draw that diagrammatically. W1 times X, W2 times Y, plus your scalar W1, W0 times 1. And say that we're going to put in three things, a constant 1, so for voltage high, you want to get in the circuit. Put in an X, which has whatever value your first feature has. And a value Y for whatever value your second feature has. Three inputs. One which is just always high and constant. Two which are measurements of features. These are each going to have a weight. Weight 0, weight 1, weight 2. Linear, we're doing linear weighting. We're going to take them and sum them. W0 times 1 plus W1 times X plus W2 times Y. And we're then going to compare that. This is a comparator. Compare that with 0. This is that less than 0, whatever the argument there is 0, that comparator. Is that if the input to the comparator is negative, the output of the comparator will be -1. If the input to the comparator is greater than 0, then the output of it will be positive 1.
If it is 0.
If it's 0, usually we put it equals there and say greater than or equal. Sometimes we put it, make it 0. Depends what you're doing. But being as the probability of them being actually equal to 0 is how much in continuous probability? 0, we don't need to worry about it. So you'd put an equal someplace in your code, but you wouldn't worry about it. Okay. Okay. 2 classes linearly separable. We can again have those weights. And we want to find an off here, instead of finding the weight where we project onto the weight to separate them. Here we are looking for a weight that will produce a vector that is the decision boundary. We're looking for a weight that will produce the decision boundary, assuming that we have a 2-class linearly separable case. What's the difference between something being linear and something being affine? You've heard that word affine before. It's all sorts of cool math in this class. Yeah.
Is it the plus constant home at the end?
Yeah, that little constant guy. A question I love to give in my signals and systems class. And some of you have taken this class, and most of you have taken an equivalent to this class. And if we have a system, y of t is equal to 3 x of t plus 1, where x of t is our input and y of t is our output. Is this a linear system?
No.
And then I torture my students in the junior class by making them actually go and prove whether it's linear or not. And to do that proof, we would take x and say that x is going to be x1 plus x2. And what would we get if we added y1 plus y2? Y1 plus y2 is going to be 3x1 plus 1 plus 3x2 plus 1. But if we put an x1 plus x2 directly in there, the constants don't match up. So in order for something to be linear, you have to satisfy additivity and scalability. From your circuits class, if you had circuits 1, you had what do you call them circuits? Superposition. If you have a circuit with 2 different inputs, you can do one input, get the result, take another input, do the results. For those of you who took circuits 1, that should sound vaguely familiar. Sorry, I'm just bringing back bad memories. So if you can do them individually, then you just add those outputs. And in your circuits 1 class, you're building circuits out of resistors, capacitors, and inductors. And those are linear circuits. And sometimes if you read the title on your textbook, it calls it a linear circuits class, even though they don't tell you what that means. Then when you get smarter, You then get to take classes with transistors and diodes. Raise your hands if you're taking a circuit class with transistors and diodes. Those are not linear circuits. So superposition no longer holds. So the difference between linear and not linear in this case is that constant, which does not match what you learned in high school algebra. Because your algebra teachers didn't really take enough advanced math. Okay. It's only linear if it goes through the origin. If it's that straight line, it's affine. AFFINE. And the difference is a constant. Sometimes it doesn't matter the difference, sometimes it does. In this sort of situation, it does. And here, if we're talking about something, whether it goes through the origin or not, it matters. And the difference is whether we have this extra constant or not.
Does affine overline with linear?
Everything that's linear is affine, but things that are affine are not necessarily linear. All that math that you never knew that you wanted to learn. It's not that bad, is it? Okay. So for Fisher, we're trying to find the weights that enable us to project onto the line. For linear discriminants, we're trying to find the weights, which will determine that line, that divide the two classes. So here's a couple of example pictures. And we're just going to take the example on the top. Take the top one. Those top lines, do you agree, separate your two classes, X's and O's. Okay. But rather than trying to say, is everything on the right side of the line, that if it's an X, you must be less than 0. If it's a Y, you must be greater than 0, and keeping track of that, we're going to simplify the math. So we're going to have our little system here. And we're going to say, if our X's are greater than 0, we're going to have a smiley face. If our Y's are less than 0, we're going to have a smiley face. So we're going to get some X's and Y's, class 1, class 2, X's and O's. And we're going to say, is our discriminant bigger than 0, less than 0? For them, that's a little bit hard. But what I can do is I can say, if negative Y is greater than 0, we're going to have a smiley face. Instead of saying if Y is less than 0, we're a smiley face, we're going to say if negative Y is greater than 0, we'll have a smiley face. I did the same thing.
Except in the case where y equals 0.
Except when Y is equal to 0, we're not worried about that because the probability of it being equal to 0 is 0. So we're not going to worry about that. We're engineers, not mathematicians. We don't need to worry about it. So therefore, all we need to do is take the y's, put them by -1, and we can do a test of everything to see if everything is positive. We don't need 2 tests. We don't need an extra if statement. So long as we take all the y's and put a multiply them by -1 before we get in there, we only need one comparator. Is it bigger than 0? Which makes everything a lot easier. Is it bigger than 0? Smiling face or not smiling face? So what we're going to do here is we're going to take our x's, x's versus those, and we're going to take each of those feature points and have a feature value of, we'll say 5 and 1. Bear with me here, pretend approximately 5 and 1. And if we negate each of those, we get a -1 and a -5. Agreed? And if this next one was a 1 and a 6, we negate that. We get a -6. And if this next one were a 7, we negate that and we get a
-7.
You guys are still with it. That's good. And so we're going to come over here and have our -1, our -5, -6, -7. Can you see how the top left picture transforms into the bottom left picture? We're going to take everything that's class 2 and negate its feature values. And now if we have a good line, everything's on the same side.
Losing track of what all this is accomplishing for us.
We're trying to choose our decision boundary. We're trying to choose a decision boundary that separates the 2 classes. The question is, what you forgot what we were trying to do at the beginning.
Not being why you would want to pull down both sides of the, have it on both sides of the line with that.
We can have it on either side, but to do that, we need to have one test for X's and one test for O's.
So
By negating one of them, we have one test. We don't need to have 2 tests. Is X greater than 0, is Y less than 0. We have one test. Is whatever I feed in greater than 0? Lot simple. We don't need to keep track. As long as we know it was a Y, negate it. If it's class 2, negate the features. Class 1, keep your features. And everything's on the same side of the line. Similar to here, we've got feature values that we then just negated. And now everything's on the same side of the line. Now this is easy to look at in 2 dimensions. How many dimensions is your project?
8.
8. Are you guys good at looking at 8 dimensions?
Nailed it.
Some of you are getting really pros at it, okay? The same idea works. Instead of a line, we have a hyperplane. And our goal is still that once we negate one of the classes in a 2-class problem, everything will be on the same side of the hyperplane. Well, let's start with 3 dimensions before we get up to 8 dimensions. And you might have had this in Calc 3. You can see I'm going to cross my fingers here.
I did take that.
A plane.
Was one of my favorite.
It's a plane, the bird plane. Can be represented by its normal. Does that sound vaguely familiar to anybody in here? A plane can be represented by its normal vector. So what's drawn here in light blue, which you might not be able to see, is the normal vector to the line. That A is a vector. Normal vector to the line. 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 These little vectors are normal vectors to the line, but the same thing would work in 3 dimensions, representing a plane by the normal vector to the plane, or in 8 dimensions with the normal vector to a hyperplane. And then what these diagrams are showing next is that there's a range, a region, where that vector can lie, which will then satisfy that all your X's and O's are on the same side of your line. And we've got some room to wiggle that. And as we wiggle it, that normal vector has a zone where that normal vector can lie, and we still satisfy all points on the same side of the line. So we want to find a solution so that all the points are bigger than 0, all the points are on the same side of the line. And often there's more than one solution. So how are we going to do this? Well, you can take an initial guess randomly. Start someplace, pick something through the origin, and then you're going to move the point away from all the points that are wrong until eventually we find the right answer. We take an initial plane. We take an initial plane, which has an initial normal vector, and that's a straight normal vector. Has a normal vector. I can't draw a straight line for mouse. Normal vector. And that point there is a naughty one. You have this big figure being on the farm herding your sheep, and the sheep's on the wrong side of the fence. When I moved to Idaho 22 years ago, I had to get a new driver's license here and had to take a little written test. And one of the test questions, which I found so strange coming from New York State, was if a cow is in the road and you hit it, who pays whom? And I'm like, what is a cow doing in the middle of the road?
Open range. I remember taking that test.
So I don't come from the city, but I don't come from places with cows in the middle of the road. In New York, they have fences. We keep the cows well behaved. But here's a cow that got loose and was out in the middle of the road. We want to bring him back home. That's the naughty one. You're all shepherds. You're going to go find them and say, naughty, naughty, we want to fix you. You're on the wrong side of the fence. So with that, there's an error vector. And we can take that error vector And we can add a portion of that vector to our existing normal vector, an error vector, adding it to our normal vector. We have a new normal vector, which gives us a new decision boundary. That should be on the, putting everybody on the right side of your fence. So rather than put the cow or the sheep back behind the fence, we're going to move the fence. By adding that error vector to our normal vector. To do this, we're going to use a technique called gradient descent. Raise your hands if you've used gradient descent before. Hopefully you've used it. Raise your hands if you've heard of gradient descent before. Just those same ones, pretty much. The good news is I kind of expected this, and so I got stuff to help work on this. Okay. Think of this as we're up on a ski mountain. And we're in a ski mountain in a blizzard. Does anybody here like skiing? I like skiing too. Brundage has been really great snow quite often. I love it up there. The little cabin up there, several miles from the mountain, so it's great to go up there and go skiing. I would hate it when it's snowing and you can't see very far. Or sometimes the light's really bad, I can't see very far. You can't get a perspective for things. But you're up on the mountain and along comes a blizzard. And you need to get down to the base lodge. Even people who don't ski understand the general idea of what's going on here. You're up on a mountain, you want to get down, there's a blizzard coming, I gotta get myself out of here. So you can't see very far. You can only see a little zone around you. So you can't say there is the lodge. But you know the lodge is downhill. It's a very well-designed ski area. It's downhill. You don't need to worry about the trees, or you can just avoid the trees. You're going to go downhill, and if you get downhill, you're going to get to the lodge. So if I'm up here on the mountain, and I want to go downhill, I can look around and say, which way is downhill? Oh, that way is the steepest downhill, and I'm an expert skier. I'm going to take the fastest route down. I'm going to ski downhill a little bit. Now I look around me. Which way is downhill? Oh, there. Now I look around me. Which way is downhill? You keep taking steps. At every step, you look for which way is downhill. You take another step. Which way is downhill? You take another step. And if you keep going, you don't hit any trees, you don't fall off any cliffs, and you're smooth, so you don't have any cliffs to worry about. You'll find your way down to the lodge safely. You can go in and have a hot cocoa or a beer, whatever you want. Okay? That process makes sense. That's gradient descent. That's all there is to it. Figure out where you are. You can locally determine the equation for what's around you. You can determine a gradient derivative. Take the steepest one downhill. Take your guess. Take a small step in the direction of the downhill. This upside down triangle is the gradient. That's just a multi-dimensional vector. Multi-dimensional derivative. And we're going to take some scale of how big of a step am I going to take? Am I going to take little tiny steps? Or am I going to take big steps? What's the advantage of taking big steps? You get down faster. What's the advantage of taking little steps? Accuracy and safety, you don't fall down. Okay. So there's a trade-off between big steps and little steps. Take too big of steps, you might go out of bounds off the trail into the trees. There's a lot of news reports about people this winter dying in the ski mountains because they ran into trees or into tree holes. So you don't want to take too big of a step downhill because you might go off trail. But if you take too tiny of steps, you're going to be up there till after dark. That's not good either. So you got to choose how big of a step to take. Now this is similar to the K&N project, where you had to choose K. You had to choose your distance formula. You as designers have options. The value for your step size is not a one-size-fits-all. It's something that you need to choose. Too big, you can run off the trail into a tree. You don't get home, you overjump things. The bigger problem here isn't trees, but it's that you're going to jump across past the lodge and start going up another hill. Not really good for a ski analogy, but if you take too big of a step, you want to get to the bottom of the hill. If you take too big of a step, you can jump over the bottom of the hill. And then you can jump over again, you can jump over again, you jump over again. You can wind up not getting where you want to go. Take too little of a step, you take forever to get down. And if there's a little tiny hill there, so you have a second local minimum, it's not smooth, you can get stuck at a local minimum. You wind up at one of those ski chalets up on the mountains and you never actually get all the way down. Oh, I have a ski chalet, it must be down. Nope. That's the idea of gradient descent. Then there's math that goes on through there, but you're going to iterate each time, adjusting your position by a step size times the direction downhill. I posted these slides. Here's some sample code. If we take an initial function, it's a straight line. We're going to say that we're going to try and optimize our cost, which is finding the best slope and intercept value. That's your goal. We've got a bunch of data. We want to fit to a straight line. We want to optimize that straight line fit. This is not related to the previous example, it's just a gradient descent example. We want to find the best line that fits your data with the correct slope, correct y-intercept. Bunch of data. We want to find the best one. We don't know what the best slope is. We don't know what the best intercept is. We don't know what the best slope is. We can say that we can take our data, which if it fits the line, would be mx plus b. We can subtract the difference between the data and mx plus b, where x is your measurement. And if we find the right m and b, this term should be 0. But while it's wrong, we don't know whether this error is positive or negative. To get around that, we're going to take the error and square it. You could take an absolute value. What's the problem with absolute values?
That's a discontinuity.
Got a discontinuity. Derivatives. We like to take derivatives, gradient descent, downhill, direction, derivatives, downhill. And so that discontinuity makes the derivative a problem. So instead of taking the absolute value, we're going to square that error. We're going to go through a certain number of iterations. If you're skiing on the hill, how long does it take you to get down? I don't know. But if you wind up out in the woods too long, you want to kind of pick up yourself on the call for help. So we're gonna set some sort of trip in our code, saying that if we've exceeded a certain number of iterations, we've got a problem. Hello, Houston, we have a problem. So this is our emergency stop. The big red emergency stop button. So when we write our iteration or algorithm, we're going to say, if we've gone more than so many steps, stop because there's a problem. We're not going to have this code running an infinite loop. We're also going to stop if we've been able to decrease our error so that our error is really small. If our error is pretty close, we're not actually at the bottom, but I can see the ski area, the ski chalet. We're good, the error is small. We're gonna stop. How small is small enough? It depends. Right answer for almost everything in this class. And who has to decide? You, the design engineer. And going back to the first one, how many maximum iterations do we want to take? What are we going to give up and call?
It depends.
It depends. You got to pick some number. You'll figure it out. And we're going to keep going. For those of you who ski, when you get down to the bottom of the hill, if it's long and flat, what happens?
Slow down.
You slow down. And so at that point, I hate trying to ski on flat things with downhill skis. Boy, it's hard. So if we're not making any change in our position because the gradient's too close to 0 and our step size is small, our estimate of where I am is going to start not changing. So if we're not changing where we're at, we're going to give up, take off our skis and walk. Those are our 3 stopping criteria for gradient descent. This is a while loop, which means while we have not exceeded the maximum iterations, while our error is not small enough, and while we're still taking big enough steps, we're going to keep going.
For the big enough step size, don't you want to wait maybe a few iterations? Because what if you're like right on a very slow descent just before a steep drop? Don't you want to maybe check a few iterations to see if you're about to drop off a cliff?
Well, notice that this eta is a function of k. It can be a variable step size.
Okay.
We also generally assume that our functions, our cost functions are, we assume that our cost functions are smooth. Not always true. But there's lots of different things we can do to change that there. Who gets to decide?
We do.
You get to. First, I want to get you through the basic algorithm. Okay. So we're going to keep iterating, keep working our way down the hill. So long as we've not taken too many steps, so long as we're not at the bottom yet, and so long as we're still working our way downhill, still making change. We're going to increase our iteration. We're going to take another iteration. We're going to calculate the derivative of our error with respect to our first variable. Derivative of our error with respect to our second variable. Together, those 2 derivatives form our gradient with respect to the variables we're trying to optimize. We're trying to find M and B for the optimal line to fit our linear points. So our gradient is going to be with respect to M and B. Our gradient's a 2-element vector because we have 2 elements we're trying to optimize. We have our formula here. Okay. And we're just going to take the derivative of this with respect to M. Get out a piece of paper. You should work this out with your neighbor. For that squared term here, what's the derivative of this with respect to m? Help one.
Just go.
That's why you can talk with your neighbors. Somebody must remember help one.
Low tech errors over here.
And negative 2mx.
Out of 17 of you, one of you must remember help one.
One was 10 years ago.
Please. Help him.
Negative 2mx. No, we assume y and b are constants, so it's just negative mx squared. You just bring down 2.
With respect to m, y, and x and b are constants.
It's just negative 2mx. Actually,
Chain rule. Remember chain rule. Remember chain rule.
Wait, what is that?
Negative 2m. It's just gonna be negative 2m times all the stuff that's in there. Or are you squaring it first?
I was gonna square it first. Don't do that.
it's so much better.
New chain rule.
I have his endorsement.
So you drop the exponent.
Yeah.
You have to add an arbitrary constant, right?
Deriving,
Not integrating. Hey, look at that.
Come on, Brett.
I know.
You expect the engineering role.
I didn't tutor for 7 years. However long.
Yeah, I better remember this.
No kidding.
Dusting some problems off. I know. You don't need to apologize. There's a reason I'm having you do this, is because of too many. I know that out of all of you, there's a lot of cobwebs. The point is, can you get them off?
2x.
Driving with respect to m. So the 2 comes down, and then the derivative, the inside stays, and then the derivative.
Yeah, that's
Shooters just calculate. So
that's the best way of learning stuff, is to tutor it.
True.
Negative 2 would just be.
So
Times,
this,
would that just be
Correct.
x?
okay. Yours looked like super long.
So.
Did you get it?
Algebra?
So this is what I got. Yeah, so you drop the exponent down to the front.
I did the exact same.
X comes out. That's also still in there.
That's right.
Yes. Yeah, because it's negative x. It's like that. Yeah. Yeah.
Yeah, that's what I got.
They're coming together, everybody?
Actually, without the y. Oh, wait, no, you're right.
So we
You're right.
take the
You're right.
derivative.
My bad. Sorry. I
2
thought
times.
the squared was just for that inner.
Yeah, this inside the parentheses is the
That's
same.
outside the parentheses.
All
So
that
on
is
the
different is
inside,
negative
y
2x in
minus
front.
mx plus b. And then chain rule. What is the derivative of stuff on the inside with respect to x? Or respect to m? Negative x. What is the
Yeah.
negative respect to B of that same quantity? You're starting to turn. So now let's look at this code. First parameter is M, second parameter is B. Two times y minus mx plus b times negative x. 2 times y minus mx plus b times negative 1. Can you kind of see where that came from? What's that sum stuff about?
For every point.
Every data point that we're trying to fit to a line. So we're going to look at what that error is for every data point we're trying to fit to the line. And this is MATLAB, so I can do it all at once with this dot multiply.
Should they both be dot multiply?
No, because this is just a scalar. This will still be a vector, but we've got a vector times a scalar. So that means dot multiply.
Perfect.
So we take these two elements together, they form your gradient. We're going to update our estimate by taking what we had before for our estimate and taking a step downhill in the direction of our gradient. We're going to update our estimate by taking a step downhill, how big the step is, in the direction of the gradient. If we're bigger than 1, if it's the first time through, we just repeat what we have. Otherwise, we're going to keep track of how much we changed. For the first time, there is no previous change. Keep track of our old parameters, update our estimate of our new parameters, figure out how much error we totally have. So what's our guess and what's our total error? Which then means we can come back up here and say, have we taken too many steps? Have we taken too many steps? Is our error small enough? Did we make a big enough change? But we're not changing, we're going to stop. What do you think about the code? Sort of makes sense how the algorithm works? So if I change the problem, what do you need to change in the code? Right now, the question is, I'm trying to fit a whole bunch of points to a line, to a straight line.
You know, what's in the while statement of the max iteration, max error, and then change.
This part's going to stay the same. We're always going to be counting our iterations. But if we're no longer trying to fit this form, these are going to change. So these have to be chosen for whatever problem you're working on. The rest of it, the little tiny bit here, I guess also changes a little bit, but most of the rest of it stays the same. So we get the coefficients, from there we can figure the line. And I'm going to hopefully. How much time do I have left? We got 5 minutes. Cross your fingers, guys. There's a bunch of points. And this is the line, we start with the sub-initial guess. It has an initial slope, it has an initial y-intercept. Our error is probably still pretty big. So we're going to keep adjusting. And it's going to gradually adjust itself, changing M and B every time. Until it's as close as it can get. Here's our surface, the points we had. Sorry. We started up here. We took a big step, then we took a bunch of smaller steps until we got down to the bottom. This surface here is the plot of this in MB space. In MB space. The paraboloid. Those are the points. We have a couple big errors and then slowly work our way down. You can see how much error we have. We're really close. Questions, comments? You will have to do this at home. I covered a couple of different things today. One is the linear discriminant. And the second one is the fact we're going to try and iterate to find the best line that can separate the classes using a technique called gradient descent. So two big concepts, and gradient descent gets used in all sorts of places. When I was a PhD student, I shared an office with 3 other PhD students. One of them was doing semiconductor stuff. I don't know semiconductor stuff. I don't know anything about semiconductor stuff. And we had a whole bunch of measurements from data, and he was trying to figure out what the parameters were to his model for all those data. And I said, why don't you use gradient descent? What's that? Well, being a signals person, I explained to him what gradient descent was. He goes, let me try it. So the next day I came in the morning, good morning, how you doing? It worked. He was able to code up gradient descent. He found his parameters for his model. They fit it really, really well. And he was very, very happy because when you're able to move forward in your PhD research, you get very happy. So that's the general what we're talking about. And we're just going to keep iterating for that. And I've got a demo for that. We don't have time. We'll talk about that next class. How's project 2 coming? How many of you have a classifier built for the case A? How well does it work? Pretty well. How many errors on your training set? That's 1. How many errors on your 2 test sets? Look up your data. You can look in.
98 and 80.
I'm planning to post the first couple columns of the sigma for A, the class dependent covariance mix, so you can check whether your sigma matches. If you're able to get a couple of the columns of sigma A correct, you probably have all the columns of sigma A correct. And if you have sigma A calculated correct, you probably have sigma C, sigma E, all the way to sigma Z correct too. I'm going to post those. You can take a look and see whether you've got them right, which should give you some feeling for parts B and C. Because if you have all of these right, then you average these to get your sigma for part B. Use it independently for your sigma for part C. Take the upper corner. For part D, graduate students
Inches. Randomize. That's
will be picking out whichever
But it took 10 minutes to code up and get
4
all.
points you
Yeah,
need
exactly.
for
Yeah.
part E, depending on which ones you're choosing. So if you can get, I'll give you 2 columns of sigma A for you to check and see whether you're heading the right direction. Any other big questions? Have a good weekend.